Section 3.5, higher order derivatives. So we're going to be taking today derivatives of derivatives. So just taking a derivative and then taking the derivative of that function. Sort of, I guess, self-explanatory in and of itself. What's more important here is that we understand the concept of what a second derivative represents. So today we're going to find and apply higher order derivatives. In order to illustrate what the second derivative means, first we'll talk about a second derivative. If you'll look at this example, Garfield said he's proud to report that he's gained only 1 pound. And then with Garfield, the goal of a diet isn't losing weight, it's slowing down the gain. So his weight is something that is being discussed. And then there's the change in his weight. And then there's also the change in the change of his weight. So that's sort of what we're going to be talking about here with the second derivative. If we let W of t be Garfield's weight in pounds as a function of time in weeks, we're going to interpret some of these labels. So W of t is the weight in pounds. So we're going to interpret W prime, and W double prime. That's hard to say. W of t would just be his weight. Now, for the unit, that would just be pounds. So W of t is the weight that you were given. When we talk about the derivative of W, we're talking about the change in weight over time. And in this particular instance, we're given that time is weeks. So this would be the change in weight over the change in time. Just like we would with any derivative, we're just talking about the rate of change over time. And in this case, the quantity happens to be pounds per week. All right, so that would be the unit. If we're talking about W double prime of t, this is where we're talking about the change in the weight gain over the change in time. So this would be the change in the weight gain over the change in time. And we'll put a unit on that as well. So the weight gain would be the change in the weight itself. If there's a gain, then the weight's changing. And then it's changing over time, so that's changing in weeks. So you're going to take the change in the weight, which is in pounds per week, divided by the change in time, which would be weeks. So the first derivative is in the numerator in this case, and then the denominator is just represented by the unit of time. So this we would usually say is just pounds per week squared, because if you multiply by the reciprocal, you bring those weeks down into the denominator. So that's kind of how we would discuss what these quantities represent in context of this example. Now, for part B, we're being asked to draw a sample graph of the quantity W of t, where Garfield is always gaining weight, but at the end, he's slowing down the gain. So he's still gaining weight. He's just doing it at a slower rate. So you would make a graph here of his weight, which is represented by W of t over time, which is t in weeks. And then the y-axis would, of course, be represented by pounds. And then if you were going to create a graph, it could look like any number of things, but this says that at some point that weight gain is starting to sort of maybe not level off, but it's slowing down. So the weight's still going up, but the gain is decreasing. So maybe it's got a little bit of a steeper slope, and then it kind of starts to get a little bit more of a shallow slope. So something like this might represent what happens if he's still gaining weight, but the gain is starting to slow down. So the rate and change of the weight gain begins to decrease, which sort of is what the second derivative is representing here. Use one or more of W being greater than 0, less than 0, W prime greater than 0, less than 0, W double prime greater than 0, less than 0 to fill in the statement below. Oh, and by the way, I keep saying double prime. Sorry, I should have specified what that was. Anytime we have a second derivative or a third derivative, the notation is down here. I was going to discuss it, but I'm using it here, so I should have specified what it was. So W double prime, of course, is that second derivative. You can say W double prime if you'd like. That's usually how I refer to the second derivative, or just the second derivative of W. Okay, so for Garfield, the goal of the diet is not to lose weight. It's just to not gain weight as quickly, or to slow down his rate of change of the weight gain. So if the goal is not to lose weight, but it is to slow the rate of weight gain, like maybe instead of gaining like 1 pound per week, maybe gaining like a half a pound, and then maybe gaining a quarter pound, so on and so forth, then we would have to represent this with symbols. So the goal is not to lose weight. So it's not about having the weight itself, or the rate of change of the weight decrease. So the rate of change of the weight being less than 0 would be losing weight. So the quantity is changing. If you're losing weight, you're talking about a quantity that's changing. If we're talking about a quantity that's changing, we're talking about a derivative. So losing weight means that you would have a rate of change that was negative. Gaining weight means you'd have a rate of change that was positive. But slowing down, changing the rate of the weight gain, would be the second derivative. So in this case, he wants that the second derivative is less than 0. That the rate of change of the gain is negative. Okay. So I know that's not necessarily, I mean, it is really a real world context, even though Garfield is not real world, he's a fictional character. I mean, you can think of a lot of different instances, even in your life. You can even think about it in terms of some sort of gain or loss of some quantity, some bodily quantity, even muscle gain and loss. So, I mean, you can think about this in practical terms. So even though it seems sort of abstract, once you get used to thinking about the idea of it, I think it'll kind of come together for you after you see some more examples, if you're still not sure. So the notation is, for a first derivative, we usually call that y prime, or sometimes we say dy dx. Now, with a second derivative, it's easiest just to say y double prime. That's usually what we use. But if you're using this notation, you would square the d in the numerator and square the x in the denominator. It's not a huge deal, but I just don't want you to use it wrong. So if you're not sure, just use y double prime. You might come across instances, though, especially in the next section where we're taking derivatives implicitly, when you might need to use this notation. So just remember what that represents. And all of these will follow the same pattern. So it says for the nth derivative, we denote it like this. That means that if you have a fourth derivative, you don't say y prime, 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 prime. At that point, you're like, okay, y quadruple prime. I guess technically people would know what you mean, but that's not how we write it. You would just say y like fourth prime of x. Not in writing, once you start to just include so many apostrophes, it starts to get really muddled, and like it's hard to add up how many there are. So that's why we stop at 3. I think it's more easy to discern 3 apostrophes between 2 and 3 and 1 versus 4, where it's just like, wait, what? That's why we use this notation. All right, so that's the notation for higher order derivatives. Now we'll find some higher order derivatives. I'll give you some examples of how to do this. I'm actually going to add an example too. We're going to just include an extra page. I'll explain that when we get to it. Example 1. So this is, we'll call it y equals the cubed root of 3x squared plus 5 squared. And we're going to find, in this case, f double prime of x, or find y double prime. Okay, so we can't find y double prime without first finding y prime. So first things first, we're going to find the derivative, and then we'll take its derivative to get to y double prime. Now, in order to do that, you have to remember, I know I've listed this property so many times, but it's important, and sometimes we forget what it means. Using the wrong variable. It's not a big deal, but I like for this to be consistent. So it's usually a to the m and then nth rooted, which is the same thing as the nth root of a to the m. Remember, we can rewrite that with a rational exponent as long as the index is the denominator of the fraction and the exponent is the numerator of the fraction. So now we'll rewrite our expression y equals, and then we'll have 3x squared plus 5 to the 2/3 power. Now for this, I'm going to need to use the chain rule. And the reason is I'm not just taking x to the 2/3 power, I'm taking a function of x to the 2/3 power. I have an inside function here. My inside function is 3x squared plus 5. So remember that I'm going to take this derivative right now, just acting like it doesn't exist for a minute, this inside function, and then we're going to chain on its derivative. So I'm going to say y prime is, I'm going to bring the exponent out front, rewrite the inside function, decrease the exponent by 1. So 2/3 minus 3/3 is negative 1/3. And then I have to chain on the derivative of the inside function. Remember that with the chain rule, I know we just went through a whole section of this, but one thing that students tend to get wrong most often, I've noticed, is this part right here. It seems really straightforward, but people forget to just rewrite the inside function and they start to take its derivative here. Be careful with this, really practice it. Treat it just like you would any problem from 3.1, but just chain on the derivative of the inside function. Initially, you're just rewriting it. You're just carrying it along. The derivative of the inside function is 6x. It will behoove us to simplify this a little bit, because when we have to take the derivative of the derivative, we just don't want to have all this extra fluff around here. There's not a whole lot I can do, and you're going to have some options here. But we certainly can. The option I was thinking is we could rewrite this negative 1/3 in the denominator as positive 1/3, and then we wouldn't need to use the product rule, but we'll still need the quotient rule. It's kind of up to you. I tend to find students would prefer to use the product rule if they have a choice, but it does not matter. I think you'd use product, so I'm going to go with that. But first of all, let's just multiply 2/3 times 6. 12 divided by 3 is 4. So you have 4x times 3x squared plus 5 to the negative 1/3. All right, so this, remember, is y prime. Y prime. I almost called it something else. I don't know why. This is y prime. In order to get y double prime, we're going to take the derivative of that function. Now, this is where students need to really understand what it is that they're looking at. Now, we still need to use the chain rule, but you actually need to use the product rule because you are multiplying some function of x by another function of x. So this needs the product rule. Now, you would still need the quotient rule if you had decided to bring this expression down to the denominator with a positive 1/3 exponent. But for right now, we can leave it as it is. We can use it with the product rule. We'll call the first factor f and the second one g. Okay, so now let's go ahead and take this derivative to get y double prime. So I'm going to take f prime g plus f g prime. So I'm going to label what we have right now. So this is f prime g plus f. And then g prime is what needs the chain rule here. So we're going to bring the exponent down as negative 1/3. I'm going to rewrite the inside function. decrease the exponent by 1. So negative 1/3 minus 3/3 is negative 4/3. And don't forget to chain on the derivative of the inside function. This whole quantity right here is g prime. So there's a lot going on here. We'll simplify it a little bit. There are a few different things that we can do here to make this look tip-top. One thing I would definitely do here at first is to just multiply 4x, 6x, and negative 1/3 together to just simplify these quantities. I'm going to leave the first term as is for right now. So I'm actually going to have a minus sign because this is negative 1/3. I'm going to have an x squared, and I have 24 divided by 3 is 8. So it'll be minus 8x squared times 3x squared plus 5 to the negative 4/3. And honestly, I'm pretty happy with this answer in general. If you were told that you needed to get this written as one term instead of two, then you'd have to do a little bit of work to it. But right now, it's pretty good. Let's see. Yeah, I mean, you could probably leave it like this. Note that your answer would come out a little bit differently if you had done this using the quotient rule instead of the product rule. You would end up with a second derivative that was a quotient. But I'm going to go through one of those with you in a couple minutes when I do the extra example. So you'll see how that works. But yeah, I would say this is probably fine as is. This is the second derivative, y double prime. Okay. All right, so let's do example 2. This will be y equals x squared over x minus 1. And we're going to find y triple prime. Okay, so we have a few things going on here. First of all, you're going to have to use the quotient rule. There's really not much of a way around that. So let's go ahead and just label this right now with f in the numerator and g in the denominator. Sorry, this like light purple is a little too light. Okay, so now we'll go ahead and take y prime. So we're looking at f prime g minus f g prime all over g squared. And we'll simplify. So I'm going to label this one, but I'm not going to keep labeling these. I think we should be pretty good with our quotient rule now. F prime g minus f g prime all over g squared. Okay, so we'll simplify. I'm going to distribute. So I'll have 2x squared minus 2x minus x squared. 2x squared minus x squared is just x squared. So we'll have x squared minus 2x over x minus 1 quantity squared. Now, you might be tempted to factor the x out of the numerator. I would not, because you're going to have to take this derivative again. And if you factor this, well, you're turning it into two factors, and one of them will be, you're going to have two different factors that include functions of x. That means that when you take its derivative, you'll have to use the product rule and the quotient rule. I would not do that. Don't turn f, the numerator, into a product. Just leave it. This is y prime. Now, when you take the second derivative, you have a new f and g. Now, this numerator, x squared minus 2x, is f, and g will be the denominator, x minus 1 quantity squared. So now we'll take y double prime. So I'm going to take f prime, and this is going to be two terms, so make sure you put parentheses around it so everything gets distributed. So there's your f prime times g minus f. G prime needs the chain rule, bring the 2 down, rewrite the inside function. It goes to the first power. Now, in this case, you only have to chain on the inside derivative, which is 1. So if you forgot to use the chain rule, you would kind of luck out here because it's not really going to affect your derivative. Now, when you take g and you square it, when you take a power to a power, you multiply the powers, and now you're going to get x minus 1 to the 4th power. But let's go ahead and simplify this a little bit. Sorry, I'm a little crooked here. Let me straighten that out for you. Straighten. There we go. Okay. All right, so let's simplify y double prime. Now, another thing I want to point out to you, notice you have a common factor of x minus 1 here, here, and here. As long as you can see that factor in each term, you can cancel out as many as you see. You could technically factor it out of the numerator. That means you can cancel it. So get rid of one of these, one of those, that whole factor is gone, and then bring this now down to the 3rd power. So it would have been the 4th power. I should have written this here. Let me specify. X minus 1 to the 4th. And then what we're going to do is just decrease that exponent by 1 and send it down to the 3rd power. Okay, now we can rewrite our simplified numerator. We're still going to have to FOIL the numerator in this case because I'm multiplying 2 binomials. So this is going to become 2x squared. And then we have minus 2x, which is minus 4x. And then negative 2 times negative 1 is plus 2. Minus, and then anything that comes behind this minus sign gets parentheses. So I'm going to take the 2, I'm going to multiply it in to the parentheses and subtract that whole set of terms off. So it'll be minus 2x squared minus 4x. Now this x minus 1 is gone. All right, so 2x squared, 4x, I'm going to subtract those off. And in the denominator, we have x minus 1, quantity cubed. And when we simplify, we'll get 2x squared minus 2x squared, which is no x squareds, negative 4x minus negative 4x, which is negative 4x plus 4x, if it helps you to see that. We'll rewrite that one more time. And you just end up with 2 over x minus 1 quantity cubed as y double prime. Now that's nice because we knew that we were going to be eventually taking y triple prime, and it was starting to get a little bit crazy looking, but this looks a lot more simple. So now we can take the 3rd derivative of this function. Now when we take the 3rd derivative, it's up to you. You could use the quotient rule. I would not. I would rewrite y double prime so that you can just use the chain rule. I would rewrite it as twice and then bring that x minus 1 up with a negative exponent. So it'll be twice x minus 1 to the negative 3rd power. And now it's going to be a much simpler derivative because you don't need to worry about using the quotient rule with the chain rule. All right, so we'll do this one more time. So now we'll have y triple prime. So we'll have twice negative 3 times x minus 1 to the negative 4th power. And then when we simplify this, we end up with negative 6 over x minus 1 to the positive 4th power. That is your 3rd derivative. All right. If you got lost at any point during that, please feel free to come to the office hour and see me. I know some of these 2nd and 3rd derivatives with quotients can start to get really confusing. The nice thing about having the video is at least you can stop pause, rewind, and go back and see like, wait a second, how did that happen? But if there's something in particular, write it down on your notes, like circle it and say, ask her, and then stay for the office hour and ask me about it so that we can figure out what's missing. All right, I'm going to do one more of these. I had mentioned I was going to add an example, and I am going to add an example. I found that my students last semester really benefited from seeing another example using the quotient rule with a second derivative. Now, I had this extra page from 3.4 from our marginal functions lesson, and it was page 16, and it was blank at the end of the lesson. So what I'm going to do is just use my page 16, but your notes should be double-sided anyway, so you could probably just use the other side. But this example is going to take up like most of the page, so be prepared to have a full extra page. You will find that this is going to be immensely helpful to you because remember I was saying in chapter 4, everything you do in chapter 4 is based off your ability to find first and second derivatives. And some of the second derivatives are going to be functions that are like this. And I want you to get some practice in chapter 3 working on these derivatives before everything you do in chapter 4 is based on their conclusions. If you cannot do these derivatives in chapter 3, you will not be able to work on any of the problems in chapter 4. So it's crucial that we do this. All right, I'm going to give you example 3. And it's y equals 2x plus 1 divided by x squared minus 3. And we'll find y triple prime. Now, in the next chapter, mostly you're just going to be looking at first and second derivatives, not third, but this is only going to give you extra practice. So we're going to find all of them. Okay. We need the quotient rule. Clearly, there's no other way to go about this. So I'm going to label this F and G. And we'll take our first derivative, y prime. So I'm taking F prime G minus F. Don't forget your parentheses. That's one of the most common mistakes here. G prime all divided by G squared. Remember, just leave it squared. Don't try to FOIL that out. You're going to end up simplifying it at some point, so leave it. All right, so F prime G minus F G prime divided by G squared. All right, I'm going to simplify. 2x squared minus 6. Now, any steps as you need to, but I'm subtracting off both these terms. So I'm just going to multiply in the negative and the 2x. So these two together, 2x times 2x is 4x squared. So this will become minus 4x squared. And then 2x times 1 is just 2x. So it'll become minus 2x. Divided by x squared minus 3, quantity squared. 2x squared minus 4x squared is negative 2x squared. And then we have minus 2x minus 6, all divided by x squared minus 3, quantity squared. Negative 2x squared minus 2x minus 6 divided by x squared minus 3, quantity squared. Okay, so you should have done these in 3.2 when we talked about product and quotient rules. All right, that's your first derivative. If you want to put like a little cloud around it so you don't lose it, that's fine. Second derivative. Now you've got a numerator that's a trinomial. I'm just wondering, is there no, this does not simplify. That would be crazy if it did, but it does not. All right, now we have a new F and a new G. F prime G minus FG prime over G squared. So F prime is going to be negative 4x. Don't forget your parentheses, by the way. You've got more than one term here. So negative 4x minus 2. That's your F prime. And then we'll take G. X squared minus 3. Don't forget that it's being squared. So that's your F prime G. No, this is the light marker. I don't know if it's so light that we can't see it. f prime g, and then minus f. Don't forget your parentheses. I'm going to keep saying that. And then g prime. G prime needs the quotient rule. I'm sorry, not the quotient rule, the chain rule. The chain rule. All right. So this was your f. And then we'll take g prime. So I'm going to bring the 2 down. I'm going to rewrite the inside function, decrease the power by 1, and multiply by the derivative of the inside function. Don't forget, you're using the quotient rule. You are not done yet. You still have a denominator that needs to be put on here. Okay, so twice x squared minus 3 multiplied by 2x is g prime. G squared is just going to be your current g, but now to the 4th power. You're taking something that's squared and squaring it. A power to a power means you multiply the powers. Okay, before you start simplifying, you're going to see that anytime you're using the quotient rule and taking a second derivative, you're going to end up in a position where you can cancel out some terms. If you don't cancel them out, you are setting yourself up for a disaster of an awful algebra issue. I don't know how else to say it. Every single term here, this is a term, this is a term, this is a term. They all have a common factor of x squared minus 3. The greatest number of times you're going to see that factor in the least number of times you're going to see that factor in any of these 3 terms is here to the 1st. So that means you can take out one of them everywhere. So the 4 is going to go down to a 3, and the 2 is going to go down to a 1. Now that's really going to help you when you go to simplify this derivative. Just be careful with your notation and make sure that you can actually read your work. I always suggest using an extra pen here. Please don't use red on your test because I usually use red to grade in. But it is up to you, whatever you need to do to see that more clearly. All right, so now that this factor is being taken to the 1st power, I can just FOIL it out normally. And so we'll do negative 4x cubed, and then plus 12x. You know, because I'm pedantic and I like to do this in decreasing order, I'm going to do the minus 2x squared first. And then we'll subtract off the next one. So you're going to take the minus sign, you're going to distribute it. When you do, all these terms are going to become positive because you've got a negative by a negative by a negative. And then all of these terms are also going to get multiplied by 4x. So they're all going to become positive and they're all going to get multiplied by 4x. So this is going to become, I might as well just drop my parenthesis right now. I know I'm so crazy about parentheses, but I don't want to overdo it here with the parentheses. So this is going to become plus 8x to the 3rd plus 4x times 2x is 8x squared, and then 24x. So 4 times 2, 4 times 2, 4 times 6, they all became positive. They all got that additional factor of x on them. Now this is still just our second derivative. And then your denominators to the 3rd power. We're going to simplify this one more time before we take the 3rd derivative. Okay. Negative 4x cubed plus 8x cubed is 4x cubed. Minus 2x squared plus 8x squared is 6x squared. Plus 12x plus 24x is plus 36x. And then I have just a plus 6 divided by x squared minus 3. Quantity cubed. Looks good. All right. You got one more derivative in you? All right. You know what I'm going to do, actually? I'm going to write down the answer for you because I feel like this is like you're understanding the process. Go through it and see if you can match my 3rd derivative. I'll give it to you. You go through on your own and see, like, does my answer match hers? Okay, but this is your 2nd derivative on your own. I'm not requiring this, obviously. Mostly what I wanted you to see was what I've already done. Find y triple prime. And I'll tell you what it equals. It's kind of crazy. Negative 12x to the 4th minus 24x cubed minus 216x squared minus 72x plus or minus 108 divided by x squared minus 3 to the 4th power. All right. It's just a lot of little tiny things you need to look out for. But like I said, in the next chapter, I'm mostly focused on the first and second derivatives. In this chapter, it's kind of like a, do you know how to do this? But let's say, I mean, I could have given you this as your original function and asked you to find the first derivative, and it would have been that. So it's basically just taking derivatives of derivatives. So I feel satisfied with this. I hope that you also feel satisfied. Okay, let's talk about some applications here. For those of you who've ever talked about physics or talked about this type of problem using acceleration in algebra, we're going to talk about the second derivative and how it relates to a position function for the height of a ball after a certain amount of time, t. So we'll do that now. I'm going to give you s of t, the position of the ball, which is negative 16 t squared plus 90t plus 175. This is going to be the height. So s of t is the height in feet of a ball thrown off a building after t seconds. Find and label v of 1. Now, I know that this was discussed. It was discussed like a few sections ago. And now I cannot remember what section it was in. And now I'm looking for it. We talked about acceleration and velocity. It was on page 29, and it was part of your notes for 2.6. And 2.6 in the last chapter when you talked about the derivative, we talked about acceleration and velocity. It was on page 29. So you were told that the first derivative was velocity and the second derivative was acceleration. We didn't really do much with the second derivative in the last section. We mostly just worked on the first derivative, but it's something that you sort of heard about previously. So it's coming back again now because it's so important for physical applications for falling objects. Either way, so v of 1 just means the velocity, which we talked about being the first derivative. So in order to find v of 1, first we need to find v of t. Now, v of t is just the derivative of the position, the derivative of s. So this is going to be negative 32t plus 90. And then for v of 1, this is going to be negative 32 times 1 plus 90, and you get 58. Now, it says find and label. So if we're labeling this, if we're talking about velocity, well, you were already told that you're using feet here to discuss the distance. So you can say that this is in feet per second, t seconds. So that's v of 1, 58 feet per second. Now, it's important to note, we'll talk about this in a minute, but our velocity is positive. So think back to what that means as far as the motion of the ball. Find and label a of 1. Oh, this should say a of 1. So in order to do that, we need to find a of t. And remember that a of t is v prime of t, or s double prime, just so that we have that notation there. But go ahead and take your velocity function and then take its derivative. The derivative of negative 32t is negative 32. The derivative of 90 is 0. So your acceleration is a constant value. It's negative 32. Now, whether you find that acceleration at t or at 1, it's going to be the same. At any point in time t, a of 1 is negative 32. And you need to think now like, okay, well, this is the rate of change per unit time. So now we're talking about feet per second. So we refer to that as feet per second squared. So feet per second squared is feet per second. So it's the rate of change per second. How fast is the rate of change changing? Is the ball rising or falling at 1 second? So we found some information about what's happening at 1 second. We found that the velocity was positive, and we found that the acceleration was negative. Now, if the velocity is positive, then that means it's heading upward. So if you were to actually graph this function, you're like, oh no, she's coming back out with her graphs again. It's true. It's happening. Okay. You know what? I bet you if I just open this curtain, put a little bit of daylight in here. All right, that's a little bit better. Okay. Your function is negative 16, negative 16x squared plus 90x plus 175. Okay, we can graph this and just get a good sense for what is happening here. I'm going to zoom 6 because I had a crazy zoom in here, and we're not going to be able to see anything if we leave it. Okay, now I graphed the position function, so you can kind of see what's happening to the position over time. Now at t equals 0, the ball is at 175 feet. Remember that x is representing time in this case. So I certainly don't need to go back in time. And I don't expect the ball to be in the air very long. You can leave it at 10 if you'd like, but I don't really even think the ball is going to be up in the air for very much longer than just a couple of seconds. But I automatically know that I go up to 175 feet at some point. So I'm going to let my y max at least be, I don't know, at least 200, and then we'll adjust. I'm going to just leave a little bit of space here. Well, we can have our y min be 0 because we're not taking the ball and sending it through the ground, right? Let's see what happens with this window, and then we'll adjust it. Because this is a skill. Okay, so you can see how the ball's heading up, and you expect that it's starting here at 175 feet because it was thrown off a building. That's where this comes in. So the 175 feet is the height of the building, and the ball was thrown. So it goes up. So we need to increase our y maximum. Maybe send it to 250 and then graph it. Oh, it's not high enough. So go a little bit higher. But I actually like this, this x value. We'll keep that. So I don't know, 350 is probably way too high. Not bad. All right, so in my window here, I have x going from 0 to 10 and y going from 0 to 350. So my window, x is going from 0 to 10 and y is going from 0 to 350. It's so good for us to be able to sort of look at this in our calculators and match this up with what's occurring in the problem statement. Now we were asked about what's happening at 1 second. Looking at the graph, and we know that our tick marks on the x-axis are representing seconds, and each tick mark represents 1 second. So what we're seeing here is that at v of 1, we're looking really at this point right here on the graph. We can even just sort of reproduce this on the page so I can write on it. Don't want to write on my calculator. Not interested in doing that. And then we can just sort of talk about this graph and what everything means on this graph. Okay, so this was, like I said, 175-ish. The ball went up. So it started at the top of the building. It went up and it came back down. I know that's not a perfect parabola, but I've my hand ran out of space. Sorry, it doesn't look that parabolic, but you get a general gist. Okay, and at some point it falls. Okay, so we're being asked what happens at 1 second. Well, 1 is just like right about here. And if I were to draw a data point up here, it would be this point on the curve. So at 1 second, we found that the velocity was positive. Makes sense. because the ball is heading upward. That indicates a positive velocity. So v prime of t is greater than 0. But the acceleration, I'm sorry, v of t, not v prime. I meant s prime and v. The velocity is greater than 0. The acceleration is less than 0 at that value. Because we have this situation occurring, we would say that the ball is continuing to go up, but the acceleration is negative. Therefore, the rate of change of the ball is increasing at a decreasing rate. So it's still heading upward, but it's got to slow down because at some point it's going to hit its maximum value. And if we could actually graph the other side of this parabola, you would see that it starts out a lot steeper. And you can see that if you include more beyond x equals 0 in your window. We started at 0. That's why we don't get this piece of the parabola, but you can always adjust your window to include that. And you're seeing now that it's steeper, 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 and then it kind of starts to shallow out, and it's eventually going to hit this maximum value where it's going to hit the top. So the ball is rising at 1 second because the velocity is positive. So we could say that at 1 second, the ball is rising because the velocity is positive. A positive velocity means the ball is going up. Is it speeding up or slowing down? Well, it's slowing down because the acceleration is less than 0. Boy, thank goodness for whiteout, huh? The acceleration is less than 0, and the velocity is greater than 0. It's slowing down because the acceleration is less than 0, and the velocity, v of t, is positive. So you can see that the rate of change of the rate of change is starting to sort of level off. Now, we're also going to look at what's happening at v of 3 and a of 3. This should say a of 3. And then we'll talk about what else is occurring. But the ball it's slowing down because it's going to reach this maximum value, and then it's going to start to head back downward. Now at 3, I've already got v of t. We found that v of t was negative 32 t plus 90. I'll write that down again. And then to find v of 3, we're just, again, evaluating that function at 3. Negative 32 times 3 plus 90. And when you evaluate that, you end up getting negative 6. And it's velocity, so it's feet per second. So you know now that at 3 seconds, the velocity is negative. Now, if you wanted to get a good sense for where that actually was, I know because the calculator will be scaled out a little bit better, but 3 occurs just on the other side of that hill. So you can see 1, 2, 3 tick marks, and then it's just on the other side of the hill that you see it starts to head back downward again at 3 seconds. So I don't know, we have not determined where the maximum is, not yet, but we're actually not going to do that in this example. It's something that we could do, but 3 seconds must occur after the maximum value because we found that the velocity was negative there. Now, it's a negative small absolute value versus the 58 feet per second. The velocity was faster. In this case, the absolute value is smaller, so you can tell it's not going as quickly. Now, it's negative just because it's heading downward. Find and label a of 3. Well, remember that a of t is negative 32 all the time. So that means a of 3 is still negative 32 feet per second squared. Now, in this case, you can see that the velocity is negative, so the ball would be falling. So to answer part G, the ball is falling. And that's because v of 3 is negative. And is it speeding up or slowing down? Well, it's going to be speeding up on its way down until it hits the ground. So at some point here, this levels out. The acceleration and velocity are 0, and then it starts to head back downward, and these values start to increase as you head down. So because we have, in this case, a negative acceleration and a negative velocity, we would say A of 3 is less than 0, V of 3 is less than 0. You would say it's actually speeding up at this point. It's going to get faster and faster as it approaches the ground. And as it hits the ground, it's going to be at its fastest speed yet. And that's just due to the acceleration and the velocity of the ball. I think it's pretty intuitive also, though. Okay, last thing in this section, we're going to interpret something. I think you might enjoy this, although I'm always wrong about what students will and will not enjoy. Suppose P of t gives the population of a town t years after 2000. Interpret the following. My page has a little hole in it here, but it should say P of 17. So we're not even asked to really do anything with a function here. I'm not giving you a function. We're just interpreting what this means. So we're talking about P of t. T is a number of years after 2000. So if t is 17, we're talking about the year 2017. And if our population is P of t, then you're being told that P is 5,000. That just tells you what the population is in a certain year. So this just means in 2017, the population was 5,000. I'm not even going to say people because it wasn't even specified. Assuming it's people, but don't know. Okay. P prime has to do with a rate of change. So we're talking about the population. So P prime would be the change in the population, and the year would be 2017 again. So this would mean that the rate of change in 2017, the rate of change of the population is 500 per year. And we would say that it's growing. So you could even say it's growing by 500 people per year, assuming it's people, just because the rate of change in this case is given to you as a positive value. Now, if the derivative was negative, that would mean that the population was decreasing. But in this case, the rate of change of the population is 500 per year. It's positive, so that means it's growing by that value. The last thing we're being asked to interpret here is the second derivative. So this is how, this is the rate of change of the rate of change. So this means that the growth rate is decreasing. So the rate of change, I'm going to write this out probably twice. So the rate of change of the change in population in 2017 is -50. And what that means is that your rate of change is decreasing. So the population growth rate is decreasing. Population growth rate is decreasing by 50 people per year each year. Per year. If you're not sure sometimes about how to write this stuff, just think about what this means in regards to units. If you know that we're talking about people per year for the first derivative, and I think that that's a little bit more intuitive for us to understand, you could say like, okay, well, people per year to talk about the second derivative. So, and it's decreasing because it's negative. So the population growth population growth rate is decreasing by 50 people per year each year in 2017. Any questions about this? Come see me in the office hour, please. I know it's a lot to unpack if it's very new to you. But that is all I have for this section. And in the next section, we're going to sort of finish it off with implicit derivatives. I don't know how much of the related rates we're going to get done. Probably not much, but at least we'll do some of the implicit derivatives before you take your test in chapter 3. So it'll be 6 sections, and this was section 5. Enjoy the rest of your day. Enjoy working on your multiple derivatives. Some of you will.